Welcome back. We're now looking at problem 2 from the sample test questions. This one's a bit of a step up from just calculating the Euclidean algorithm. We have a Chinese remainder problem with 3 congruences. X is congruent to 1 modulo 7. X is also congruent to 2 modulo 11. And finally, x is congruent to 3 mod 13. And we want to find an integer x, or really a class of integers, that will solve all 3 of these congruences at the same time. The method that I've taught in this class is to take each of these moduli, and for each one, so integers mod 7, integers mod 11, integers mod 13, we're going to calculate certain multiplicative inverses. So the first thing I do for integers mod 7, I take the other 2 moduli, 11 and 13. I multiply those 2 numbers together, and I need to find the inverse of whatever this product is. And I've calculated that out, and I got 5. I'm going to go ahead and do that for the other moduli too. So for the integers mod 11, I try to find the inverse of 7 times 13. I get 4. For the integers mod 13, I find the inverse of 7 times 11, and I got 12 for that. These are the ingredients that I'm going to put in my formula to find the answer to this problem. My x has the following formula, and it's defined up to integers mod 7 times 11 times 13. So I take the number 1, which is the residue that x is supposed to have modulo 7. I take 1, I multiply by 11 and by 13, and then by 5, which is the inverse of 11 times 13 mod 7. The reason I do that is when I hit this formula with integers mod 7, right? If I take this formula, mod out all the 7s, there's a 7 here, there's a 7 here. The only thing that I'll see in integers mod 7 is, this highlighted stuff is what goes away. What I'll see mod 7 is just this formula. I'll have 1 times 11 times 13 times the inverse of 11 times 13. So that'll just be 1 mod 7, and the rest of this formula will just drop out. I do the same thing for my second modulus. So I'm supposed to have a residue of 2 mod 11. I multiply by both 7 and 13, and I multiply by the multiplicative inverse of 7 times 13. So I'll have 2 times 7 times 13 times 4. When I look mod 11, I'll only see the product of these 4 numbers, right? I have an 11 over here. 11 is 0 mod 11. I have an 11 over here. 11 is still 0 mod 11. 2 times 7 times 13 times the inverse of 7 and 13 is 2 modulo 11. And finally, for the integers mod 13, I'm supposed to have a residue of 3. I multiply by the other 2 moduli. 7 and 11 are not supposed to see this part of the formula. I multiply by 12, which is the inverse of 7 times 11 mod 13. And these 4 numbers I put together in a product. So my x is the sum of this product plus this product plus this product mod 7 times 11 times 13. So any Chinese remainder problem that we're trying to solve is only solvable up to modding out by 7 by 11 by 13. So I'll clean up this bit, multiplying it all out, adding it up. I get 4,215, and the modulus, 7 times 11 times 13, is 1,001. That's the basis for some pretty cool mathematical party tricks too, but that's not what you're here for. I can go ahead and reduce this. I'll say that 4,215 is congruent to 211 modulo 1001. So really, either of these two numbers would solve all three congruences, but this will be good enough for marks on the exam. So you'll need to show me what moduli you're using, where you have calculated your inverses, what those inverses actually are, and spell it out what is the final formula for the x that is your solution. So it would not be enough, for example, just to say x equals 4,215. That would be partial marks at best. Again, let me know if you have any questions with problem 2, and I hope that you all got either 4,215 or 211 or anything that's congruent to those as your solution.